Hi, Professor. I actually got a question in a little bit, but I'm going to wait for my wife to get home in about 10 minutes
Okay.
in case I get interrupted. Just
Well,
here recording in case someone else has a question so I can upload it later.
okay.
Actually, I'll go ahead and ask it now. Since I'm recording,
Okay.
if I get interrupted, I'll just watch it later if it's not a problem.
No problem.
So I was going over the course notes on Udacity, and on the advanced caches lesson, there's a line that says here under real VIPT caches that cache size must be less than or equal to the associativity of the cache times page size. Could you explain why that is?
Yeah. Okay. So it's because of aliasing. So if you remember what aliasing is, it's basically that. I mean, first let's go to kind of the virtual versus physical address aliasing. So essentially, multiple virtual addresses can map to the same physical address, right? And that's a huge problem for cache coherence if we are using the virtual address in any way. The reason for that is that basically if we start looking up in the cache by virtual address, if there are two versions of the same physical address, but they end up being placed because of the sets and stuff like that in different sets, then we essentially have a problem of there could be two versions of the actual same data in the same cache, and that means we need to keep those coherent too, and that's a problem, right? Because basically if I give you a virtual address, you need to translate it to a physical address and then find all of the versions of that in among the virtual addresses that are in the cache, right? So the real problem is basically that if it's a big cache and the virtual address essentially maps to several physical addresses, and I mean two virtual addresses map to the same physical address, right? But those virtual addresses end up going to different sets. That means that when we do a lookup and write to, like we use virtual address A to write to the data, but there is a virtual address B that represents the same data because it's the same physical address. So what should be happening is when we write to A, B also gets updated, right? Like we can write A and then read B and get the data we just wrote to A. Okay. So if A and B map into different sets, that means that what we would have to do is after we write A, we need to essentially find all of the other places in the cache where something that is in the same physical address would be mapped, and replace the data too, because physically in the cache the line stores a block, and physically in the cache if I write to one line, the other line that should have the same data doesn't automatically get updated, right? So the only solution that works really well for caches is if this cannot happen. So basically, if you have a situation where a given physical address can only possibly be in one set in the cache, then we don't have this problem. Because when we write to that version, that's the only version that can possibly exist, right? So there are really like three solutions that would do that for us. One is if we completely use physical addressing in the cache. So basically, if we translate to a physical address and then use the physical address to access the cache, then this problem doesn't occur because any other virtual address that we use for the same physical address would just map to the same physical address, which means now, as far as the cache is concerned, that's the same address. It goes in the same place in the cache. So the problem of kind of keeping these versions of the same data coherent with each other doesn't appear simply because there is only one version as far as the cache is concerned, right? The second option is basically that we do some sort of a multi-version thing where essentially the cache has multiple versions of the same physical address, one for each of the virtual addresses that map to it, and we somehow remember, for every physical address, where are all the virtual address versions of it, and then when we do a write to one, we say, oh, we write to this line in the cache, but we somehow know which other lines it could map. I mean, which other lines should be updated to, and then we do an update for that. That's extremely difficult to do and very expensive. The only solution that kind of works well is basically if the set is if all of these versions somehow map to the same set, right? Because we are searching the set anyway, right? And because we are searching the set, the whole, so like given a virtual address, we will search the whole set anyway. That's because of the essentially, we don't know which line in the set could possibly have this data. So if there are multiple versions that all represent the same data, but they're all in the same set, then we will find all of them, and that means that now we know which ones to update, because basically we just do the write to all of them, right? And the third possibility, which is what we usually want to do, is essentially if multiple virtual addresses can map to the same physical address, but somehow they need to end up, but there needs to be only one version in the cache. So we want it to be kind of like, we don't want to do physical addressing of the cache, but we want to have the same effect of essentially the data, a given physical address can only be in one place in the cache, so that we don't have to look for other versions, right? And to do that, if you use, okay, so first of all, this cannot be done with pure virtual indexing and tagging in the cache, because if we do virtual indexing and tagging, what happens is we don't even know which physical address this mapped to, because we don't need to do the address translation for this, right? So essentially we will access version A and not even know that that there might be version B that maps to the same physical address. However, we don't want to do full physical addressing of the cache either, because if you remember that, that automatically eliminates this problem. But the problem is that way we have to finish page translation before we access even level 1 cache, which kind of prevents us from in parallel accessing the TLB and the cache. So we kind of want something that is begins the access virtually and ends the access with a physical address, which sort of means that you do want to use virtual addressing and physical tagging. This allows you to basically parallelize a large part of the TLB access, because you can do almost all of the cache access while also doing the address translation. But then eventually you finish the address translation before the cache access is done, and what you do is you take the physical page tag, and that's what you use to compare against the tag in the cache. So basically the cache, essentially the set number is from the virtual address, but the tag is the tag from the physical address, right? If you, okay, so basically that's what you want for the level 1 cache, right? And because you have the physical tag, you are now able to check which physical address this maps to, right? So now the idea is basically with the cache size and so on, the idea is essentially what you want is, regardless of which virtual address you have for the same physical address, they all map to the same set, right? And now if you look at how we break down the address, into the tag and the set number and the index in the line, what you really want is basically that the set number has to be the same no matter which of the virtual addresses that map to the same physical address am I using, right? Unfortunately, the page offset is the only part that is guaranteed to be the same. Why? Because basically, if I have a virtual address, it can only map to physical addresses that have the same page offset, right? Right, because essentially I'm translating the page number, but the page offset always is just directly comes from the virtual address with no translation. So essentially, if I have address number 3, it has to be a physical address 3 plus integer number of pages. Simply because I can only map entire pages, I cannot map kind of with an offset within the page. Okay, so if I want to ensure that any physical address, any virtual version of the physical address maps to the same place in the cache, that means that they all need to map to the same set. And because the only part that they're guaranteed to have equal is the page offset bits, that means that the whole set number in the address needs to come from only the page offset bits. Okay, so now if you look at the how the address is composed, basically, let me just kind of do this. So essentially we have basically the bits of the tag. I'm gonna just so we have something like this. Okay, so there is basically the upper bits of the tag, the lower bits of the set, and then the offset, right? And now what we have is essentially, as far as the address translation is concerned, there is the page number and the page offset. Okay, so this is kind of how the page translation is working, right? So now if you look at it, like what we really want to have is basically that the entire page number needs to be in the tag. If any part of the page number from the virtual address ends up in the set number, that means that the multiple virtual addresses for the same physical address could be in different sets, simply because one can have a, let's do a little kind of experiment, right? But let's say I have the tag set and offset are, let's say let's just call it 4 bits, 4 bits, 4 bits. It's a very small address space. Basically, it's only 12 bits. Okay, let's say that let's do this. Okay, let's do 888. Okay, let's say that as far as that the page size is 12 bits. Okay, so basically for the virtual address, essentially, because this is 8 bytes, there is essentially 12 bits of page number and 12 bits of page offset. Right? So if we have a situation where the line is 8, the line offset is 8 bits, which means there is 256 bytes, then there is 2 to the 8th set, so we need 8 for the set number. What will happen is basically that 16 bits of the virtual address. So essentially we have that the 16 bits of the virtual address are used for the set and the offset in the cache, right? But that means that there are 4 bits from the page number that are used as the set number. Okay, and that means that there are basically a lot of possibilities for, there is essentially more than one possibility for essentially which set could this physical address map. Depending on exactly which virtual mapping we are using, the same physical address can end up essentially in 16 different sets. 16 different sets, right? Because essentially 4 of the bits in the set number are coming from the virtual address, and the other 4 bits are coming from also the virtual address, but the part that is the same in the physical address, right? Okay, now if you consider okay, what happens if I have something like 1248 as the breakdown for the indexing into the cache? Then what happens is I have only 4 sets, 2 to the 4th sets, there is only 16 sets. But now the set number entirely comes from the page offset. And that means that no matter which virtual address I have, for a given physical address, all of its versions will be mapping to the same set, simply because the part that all the virtual addresses have the same is going to be the part of the address that all of the virtual addresses have the same is the only part that I'm actually using for the set number, right? Okay, so now that we have this, we're saying, okay, so this means that basically the set number plus the line offset. So the set number plus the line offset need to be smaller than the page offset, like this. Actually, they can be smaller or equal. Okay. Why? Because basically, all of the bits for the set and that implies also for the line offset essentially need to come from the page offset. Why? Well, because if I had more bits than that, then essentially some of the bits for the set number would fall out of the page offset, and that means that different virtual versions will have different bits there, right? And if you look at this, what is the set number? I mean, what's the number of sets times the so the number of bits for the one and the other? It's okay. So the number of bits for one and the other, basically, if you look at it like what is it? It's really the size of one of the ways in the cache. It's essentially the line offset is basically 2 to the 2 to the line of the line offset is essentially the size of the line. 2 to the number of set bits is basically the number of sets, right? So essentially, if I have a direct map cache, that means that the whole cache needs to be less than or equal to the page offset, because the number of sets times the number of lines needs to be less than the page size. Is that okay? Okay. Okay, so basically that means that with a given associativity, if I want to avoid aliasing with this, the cache size cannot be larger than the page size times the associativity. The only thing in this equation that we are still allowed to increase essentially is the number of ways in the cache, because the size per way is determined by basically the line size and the number of sets, and unfortunately those two need to be constrained to the page size. So essentially, if you want to have a large level 1 cache without aliasing, you are essentially forced to increase associativity. That's the only thing you can increase, right? So if you have, let's say 4 kilobyte page, that means that each way in the level 1 cache can only be 4 kilobytes, which means that basically the only way to get an 8 kilobyte cache would be to have 2 ways. Or if you want a 64 kilobyte cache, you need 16 ways. Okay, so that's the reason why this is so. Basically, it allows us to avoid the aliasing problem within the cache. It allows us essentially to kind of still have a virtually indexed cache and yet not have to deal with the aliasing problem that using the virtual address implies. Okay. Yeah, I mean, another way of dealing with this problem, I mean, the only kind of other kind of circumvent this whole thing would be essentially to use larger pages. But unfortunately, because of legacy concerns and stuff like that, that's a problem, right? Because if you've had a 4 kilobyte page, you cannot just willy-nilly decide, oh, from now on the pages are 8 kilobytes, because a lot of the things I mean, a lot of software basically, instead of, there is a way, like, for example, in Linux, you can ask the system, what's your page size for this application? And then just, when you try to map, I mean, do mmap or something like that, where you basically, mmap, for example, has to be done at the page granularity. And if you request a specific address, it has to be a multiple of page size, otherwise the mmap will fail and stuff like that. But unfortunately, file systems and all sorts of things, in the code, people have been, for a given architecture, kind of assuming for too long that the page size is 4 kilobytes, and that means that basically it's now difficult to change. So essentially, what you can do is say, oh, the page size can be 4 kilobytes for legacy applications, and then it's gonna be something else for non-legacy applications, right? But because the physical cache, the level 1 cache, still needs to not have aliasing even for the smaller page size, you're stuck basically with using 4 kilobytes for that. I mean, 4 kilobytes per way for that, simply because if we are using 4 kilobyte pages, then we have the aliasing problem. Does that kind of answer the question?
Yeah, it does. Thank you.
Okay, no problem. Yeah, it's one of those kind of relatively tricky things. Like, I mean, the whole aliasing problem basically exists because multiple virtual addresses essentially can map to the same physical address. And now, the next good question is, so why would you allow that? I mean, what's the use case for having that? But unfortunately, the use case is that if you want to, for example, allow memory mapping of files, which says basically, I can ask the operating system, to, instead of me doing reads and writes to a file, I can ask the operating system to basically map that file into my virtual memory such that writes and reads from that region of memory directly translate to essentially modifying the file. And in most operating systems, you can do that. But then the idea is, okay, if I can map the file once in my address space, why not be able to map it twice? So essentially, if I map the same file into two separate regions of memory, the way this is really implemented in the operating system is basically the pages that are caching the file are just mapped. Essentially the memory mapped page that I have is essentially the buffer for the file that the operating system has. So if you map the file twice, what that is doing is essentially the same physical pages that are storing the contents of the file are essentially mapped into both places, and then you have the aliasing problem. You also have shared memory. Like if two processes shared memory, then again, you can essentially the way shared memory is done is basically by either mapping a file or mapping a what they call anonymous file. So basically, you just say, okay, there is no real file on the disk, but we are both mapping the same file. So there is essentially just a file handle that like I create a file that doesn't really have a physical file on the disk that stores it. And that file, let's say it has a megabyte, and then I give you a handle to that file, and then you can map that into your memory, and now we are sharing memory, right? I mean, that's how we create a 1 megabyte region of memory to share. But again, if you can map this handle once, what's preventing you from mapping it 10 times, right? Which means now you have 10 virtual addresses that all map to the same physical memory content. And then there is another problem, which is kind of like coherence within the same process. So basically, what you can have is essentially one process, does something and caches some data, and then basically the operating system switches to another process, right? And if these two processes have been sharing memory, then again, the virtual address that they're using for the same physical memory is almost certainly not going to be the same. Simply because if I do an mmap, the system gives me the address to which it mapped, and if in my address space it found a free region of virtual address space somewhere, and for your thing it found it somewhere else, then basically we are sharing the memory, but we see the same memory in different places in our virtual memory, which means now that if you have written to it and it's still in the cache when my process gets scheduled onto the processor, if I start reading, we have the same problem of aliasing, right? Because basically, if my reads are not finding the version you wrote in the cache because it's somewhere else in the cache, we have exactly the same problem, only with two different processes. So that means that even if we say, oh, a process can map physical memory only once in its address space, it still doesn't resolve this problem. So essentially, the only way this would be solved is by either not having aliasing problems, or by basically every time we do context switch from one process to the other, we need to essentially kind of invalidate the entire cache, because that way I'm sure that what I read comes from physical memory, and what you wrote was written back there, so that essentially I end up reading the same data that you wrote. But that's really inefficient, because the time slicing is such that like every millisecond or so, let's say I'm switching between processes, and that means that I will have to flush the cache a lot. Like a lot of the time, the processes will be kind of right after the context switch really slow because they have a lot of cache misses, and it's not a good idea to do that. So pretty much not having the aliasing problem kind of solves that problem too. So pretty much if you don't have the aliasing within the cache, then essentially you can do kind of the normal operating system stuff, like the memory mapping can just happen as if we didn't have caches. It is creating problems for level 1 caches though, because basically page sizes are relatively small, but that means that essentially each way of the level 1 cache cannot be very large. But on the other hand, you don't want the level 1 cache to be too highly associative, and the reason for that is it becomes a slow and energy hungry cache. Remember that we need to essentially check the tags of all the lines in the cache when we are having even a hit, And that means that if you have a direct map cache, you're just checking one tag. If you have a 16-way cache, you're checking 16 tags for every access to the cache, even hits, right? And that means you don't want the level one cache to be too associative because it creates other problems. So essentially, it is a trade-off basically. That's and part of the reason why we don't have something like pretty large level one cache is precisely this. I mean, the cache, you know, the only way for it to be really fast and still, pretty large would be if it was direct map, but you don't want that, because then you have aliasing. But on the other hand, if you have a highly associative cache with relatively small each way is relatively small because it needs to fit in the page size. Then the problem is it becomes slow, very slow, and very power hungry. So it's that's part of the reason why you haven't been really seeing a steady increase in level one cache sizes. I mean, we have seen some increase, but basically that came just because the modern processors essentially are not really growing in clock frequency anymore that much, but the circuitry is actually becoming faster. So you're now able to, within one cycle, actually do a set associative lookup. And then there are also some new architectural tricks that they're using to reduce the energy consumption when you have a highly associative cache. One of the ways is really simple. It's basically you can guess which way should be a hit if it's a hit. You look there, and if you're right, you only did one tag check and had a hit. So basically, most of the hits are essentially doing only one tag check. But if you don't find it there, then you do a normal lookup to see if you have a hit anywhere else in the set, because you cannot go to memory until you have actually checked whether you really have a hit. So the idea is that now there is kind of this is called way prediction. So basically, you're kind of predicting which way to access and just using that. And the idea is to save energy, right? So essentially, now you kind of have three kinds of things that can happen in a given cache. One is a way prediction hit, which is the most energy efficient and fastest because you actually just do the first lookup. Then you have a way prediction miss that is a hit, which means I try to check one tag, it doesn't match. Now I need to check all the tags. It takes a little bit longer, but still relatively fast. And then I have a hit. And then you can have a normal miss, right? So somehow why this is good is that basically it allows you to increase associativity without a kind of proportional increase in power consumption, but it does come at the expense of essentially the rest of the hits are now a little bit slower than they used to be, because basically a kind of non-prediction, I mean, kind of prediction miss that is a cache hit essentially now requires really two tag checks. One for kind of check quickly the first tag, and then if not, then do the normal tag check. So basically, the normal tag check is already slower than the just check one tag kind of a procedure, and now you need to do both kind of in sequence, because if you want to save energy, you really need to be checking only one at first. So you're still the only one in this office hour, so you might as well ask.
Okay.
Is it that you told everybody you will be recording?
I don't know.
No, because if you told them, it might be like, oh, I'll just like look at at the recording. I don't have to actually come. But the problem is that then we don't have kind of a diversity of questions just because only one person ends up asking all the questions.
I think it might be. Most people are in North America and they're probably still at work at this time, but I'm in
Oh, I
Europe.
see. Yeah,
It's late here, so I'm free.
yeah.
Um, if I can, I do have a question about one of the Udacity quizzes, but you might need to look at it. Am I allowed to ask you about that?
Can you just tell me which? I mean, I cannot really, because by the time I log in and everything, and they change the like layout every so often. So by the time I figure out where it is, so if you can just like ask, or paraphrase it.
Okay, I'll try. It was on the DRAM access scheduling quiz,
Uh huh.
and I really didn't understand the beginning. Hold on one sec. Let me look over it really quickly, and then I'll try to paraphrase it.
So let's see if we can addresses. Let's assume how long do they take if we do them in this particular order.
Okay, so the question is actually about cast misses, but I was really confused in the beginning. You, I guess, state that there's a DRAM. The DRAM has 32 1-bit arrays, and then you say each array is a 1 megabyte 2 to the 10th by 2 to the 10th, and then you erase that and then wrote that each array is a 60 megabyte 2 to the 12 2 to the 12, and I was really confused as to what's going on there. What are these two arrays and their relationship to each other and the whole DRAM thing?
Okay, so I managed to actually open the
long
you
do they
know the
take
is it a
if we do
lesson
them
on
in
memory, right?
Yes.
Okay, so which quiz are we talking about? The DRAM access scheduling quiz.
Yeah, number
Okay.
12.
Okay, so now how do I start the quiz without listening?
So let's.
Okay, I can quiet it down. So which part of it?
Okay, so I understand your answer and how you got it, especially when you break it down with the row addresses and column addresses. I just don't understand these givens. If you can watch the first couple seconds, you first start saying there's an array that's 1 megabyte and it's 2 to the 10th by 2 to the 10th. And then you erase that line in the video and then write each array is 60 megabyte to the 12th by 2 to the 12th. And I don't understand why.
Oh, let me check. Okay, so I'll have to view the okay. Let me just listen to it because I mean you're the only one here.
Some DRAM access scheduling to take a.
Okay, view intro.
Let's look at the solution to our DRAM access scheduling quiz. So we have 32 arrays, each is 16 megabits and takes a 12-bit row address and a 12-bit column address. 12 bits is 3 hex digits. So the row address will be the upper 3 hex digits and the column address will be the lower hex digits. Each of these corresponds to a 32-bit memory location. So what happens is each of these arrays sees the same address, but it provides a different bit for that address. So each address will have the same sequence of row and column addresses, it's just that they will implement different bits of that address. So what we have here is the first one, of course, needs to be a page open. So we have 10.
Okay, so which part of this is so basically what's happening in the quiz is essentially we have I mean DRAM is really organized as basically kind of several addressable entities, right? And each of these is essentially an array that provides some bits of the actual data worth, because we are never really looking up like one bit of memory, but the chips oftentimes are not like 32 bits wide. So basically what will happen is, let's say you have chips that are 1 bit wide. Then what you do is to do a 32-bit memory. Essentially what you do is you basically take 32 of those chips, you basically provide all of them with the same address, but the data line you connect each of them to a separate data line, and there is 32 data lines. So that's how essentially, so each of them is basically just like a 1-bit memory, and you need 32 of them working in parallel to implement a 32-bit array address. So essentially the setup for the DRAM has 32 1-bit arrays, and then each array is 16 megabits organized as a 12 kind of 12-bit by 12-bit matrix. I mean 2 to the 12 times 2 to the 12 bits matrix. What this means is essentially that it's a 32-bit memory with a 16 megabit address space, where I mean 60 megabyte, or actually 16 mega words address space, where basically, as far as each of the 32 chips is concerned, essentially it's a 1-bit memory with a 16 meg addresses. But when I address one of the 16 mega words, each of the bits basically is addressed with one of the 16 mega addresses. I mean the same 16 mega space address is provided to each of the 1-bit memories, and each of them just provides one of the data elements in the 32-bit word. That's a very typical organization actually, and the reason is that when you're building memory chips, if you want to have a lot of data and addresses, typically what you have is like you want the data to be pretty wide, and you also want to have a lot of bits inside the memory chip. So the problem is basically that in order to increase the density of the chip, meaning put more stuff on it, you need to increase how many bits the chip has, and there are two ways of increasing that. Let's say you want to double the size of the memory in the chip. Let's say that the technology has advanced, and now the same way that I was making my old chips, now I can cram twice as many bits onto the chip, right? So basically, putting twice as many bits involves either widening the memory, meaning it's the same number of addresses, but now each address is wider. So each address gets me a wider data word. So let's say I started with a 1-bit memory, and then now I have a 2-bit memory, but it has the same number of slots, right? When you're doing that, if you have a 1-bit memory and you added another bit to it, now the data lines have to be basically twice as big, right? So if you go from 1 bit to 2 bits, you're adding basically 1 bit to the data lines. If you are changing how many addresses does it have, so let's say the option is basically keep it 1 bit but increase the number of addresses, or keep it or double the number of bits. When you go from 1 bit to 2, you are adding 1 bit of data lines, or you are adding 1 bit to one of the addresses, the row or column address, right? So it's kind of like the same, right? But once you have 2, to double that, you would need to add 2 more data lines. Whereas to double using the address, you actually only need to add one more bit to the address line. So pretty much once you have some relatively small number of data lines on the chip, you would need to essentially add a lot of pins to the chip to increase its size by a small factor if you're increasing the width of the word. Or you can add a very small number of address lines, because the capacity of the memory is pretty much the width of the word times 2 to the number of bits in the address times 2 to the bits in the number of bits in the other address. So essentially adding a bit of the address essentially doubles the size of the memory of what my memory can be. Whereas to double the size by extending the word size, you actually have to add twice as many data pins on the chip. And you want your chip package to be very small, which means that if you already if you have like a 32-bit and you want to make it 64-bit, you need to add 32 pins. If you, however, want to double the size of something that only is a very narrow thing, you basically just add 1 pin. So that's part of the reason why, if you look at like the DIMMs and so on, you usually have multiple chips on them, and the reason is that every chip is providing only a small width of the word, but all of the chips are kind of acting in parallel. So basically, each of them has a lot of slots in there, but each of them is providing only part of the kind of the data width that the whole DIMM is capable of. Right, so that's the reason why basically it's like organized like this typically. So essentially, what you now have is essentially just there is a whole bunch of individual narrow memories that are acting in parallel to provide the illusion of basically a memory that is essentially n times as wide in terms of how many bits are read in parallel or written in parallel, but has the same number of addresses. Right. So that's kind of the why there is a kind of 1-bit arrays and stuff like that. Basically, what this is essentially it's a memory that is 32 bits wide and has 16 mega words, where the address we provide is always for the word. We don't address individual bits. And I mean, is that the kind of initial part that you were worried about, or something else?
That was part of it. But also, okay, right after you wrote the DRAM, first you start writing each array is 1 megabit to the 10 by 2 to the 10.
Oh, I see.
And then that disappears, yeah, and you overwrite it with.
Okay, yeah. It was possibly just the video editing, basically, because I was kind of trying. I mean, I was trying, several options here, and the real problem, basically, I mean, it's a mistake, basically. The reason why it shouldn't be there. The reason I mean, these videos, I've kind of recorded them once, then kind of worked out to like why doesn't it work and stuff like that, and then re-recorded some of them. So I think this one I tried with 1 megabit, but the problem is the address then is essentially it's a 10-bit row and column address, which means that when you write them down in hex, it kind of breaks the one of the digits in half, and that's really hard to explain and stuff like that. So basically, I went with then I kind of increased it so that essentially each of them is 12 bits, which means it's kind of an integer number of hex digits. So you can just kind of take a hex number and split it in two, rather than kind of have to, given a hex number, figure out what the two halves are. See, I mean, see what I mean,
Okay, that explains it. Thank you.
Essentially, a 20-bit address would be 5 hex digits, where when I break it in half to get the column and row address, the middle digit of the 5 digits would basically have kind of 2 bits go to one and 2 bits go to the other one, which kind of just complicates things. This way, basically, each of the 12-bit parts just gets 3 of the hex digits, and I don't have to, do any bit manipulation to essentially split them. So it's a lot easier to explain. Basically, it's just kind of doing a problem like this when the bits are kind of unevenly distributed means that you have to get the hex number converted into binary numbers before you can do anything, and that just consumes time. That's also why, like in exams, for example, very often I'll have kind of if there is some number of bits, it's gonna be like a multiple of 4. And part of the reason is that if you need to split the bits in any way, like for example for the offset index, set index and tag, it's a lot easier if you just basically say, oh, the first hex digits are just let's say it's a 8-bit offset or a 4-bit offset, then you just take the appropriate number of digits and say this is my offset. If it was like a 3-bit offset, then you'll have to worry about which bits from which hex digit go into which one of them. So I think the 1 megabit thing was basically just something that should have disappeared in editing but didn't.
All right, Professor, since there's no one else really joining the meeting, I kind of have a question I've been wondering about that's not really directly related to the course material. It might be kind of silly. Can I ask you, and if you find it too irrelevant, you can wave it off, but maybe you could answer or provide some insight?
Oh yeah, I see what you mean. In the setup of the quiz, basically, I kind of write 1 megabit, it's 10 by 10, and then it kind of gets deleted, and it's 60 megabit. Yeah, it's should have just kind of should have just gone from like each array is, and then just continue to 16 megabit. That's kind of like a video editing mistake.
So Professor, since there's no one else joining this meeting, I do have a question I was wondering about that's not really directly related to this course though, but I think you might be able to provide some insight.
Okay.
Can I ask it? And if it's, I don't know, too naive or irrelevant, you can just wave it off.
Okay. Sure.
So one of the reasons why I actually want to take this class was to learn more about the low-level architecture stuff. If that would help me in optimizing, my statements in everyday development and coding. And I did see in one of your lectures something interesting. Normally when I do a for loop, I think a lot of people do this. They iterate. They start, at 0 and go up to say 10. Have the condition checking if it's less than 10. I saw in one of your videos you started off at 10 and decremented instead of incrementing. And I kind of looked that up online, and people were saying that, yeah, technically that is a more optimized method because of the assembly. There's an instruction that checks if something is 0 or greater than 0, but if you're checking against, say, a value that's 10, there's no assembly instruction for that, so you're going to have to allocate a register and check against that. But then they're saying that, actually the compiler is probably going to pick that up and make that optimization improvement, so you don't really have to worry about it. That was just an example, but I was wondering, since you're the expert, are there statements like that that you see that maybe people often do, but you knowing a lot more about assembly and low-level workings of processors, if there's, I guess, common mistakes do you see people making every day that people could actually change the way they write their code to make their programs more optimized and performant?
Yeah. So yeah. I mean, compilers have gotten pretty good at So the idea is basically that you have this kind of common, patterns. Like for example, it's very common to have a for loop that starts at 0 and goes up to some value, right? And the compiler knows how to take that and essentially say, oh, I mean, it's kind of like a very kind of template-based transformation where you say basically, okay, instead of having a counter go from 0 to something, I'll make my counter go down from that something to 0, as long as there is nothing in the loop that basically needs the counter value itself, right? So for example, it's more optimal to do it that way if you essentially have my iterations go from, let's say, from 0 through 1000, add something to a sum, like for example, there is 1,000 array elements and I'm just summing them up, right? So basically what you normally would do is essentially when you write your code, you will write your code as for I equals 0 through 1000, take a of I and add it to the sum, right? So the literal translation of that would be basically start I at 0, and then the loop would be checking against 1000 to see whether it reached it, right? And then to index a of I, you would have to basically do something like, let's say a is a array of let's say 4-byte numbers, 32-bit numbers. You would have to essentially do something like multiply I by 4 or shift it to the left by 2 bits, right? To multiply it by 4 and then add that to the base address of A and use that to index memory so that you can do a load and do that, right? So the compiler basically very quickly will do, very quickly people who write compilers have realized this is a really common thing that people tend to do, and it's almost always like this. It's almost always start at 0, go up to somewhere and index the array with that thing, right? So basically what they will do is typically they will say, okay, the way I'll implement this is basically gonna be I'll separate the I and the index of the element. So essentially, rather than take I and multiply it by 4 to get each of the indices, what I'll do is I'll start with the base address of A, and that's going to be kind of my pointer, and I'll basically increment the pointer by 4 in each iteration. Okay, and then I'll do one of two things. So either I'll also decide that, oh, I know that A has, that I'm accessing 1,000 elements of A, so I'm going to compute what's the last element of A that is going to be handled this way, and then essentially start at the base address of A, keep incrementing the counter by 4, the pointer by 4, and instead of checking for I reaching 1,000, I'm checking for basically the pointer reaching the beyond the 1,000 element of A. So that's that way you need two registers, one to store the the pointer, but you needed a register for I anyway. You need an extra register because you are now comparing against a very specific address to terminate the loop, but you needed that value for 1,000 anyway. so somehow in this way, if you only have a loop like this, basically you will but you will very efficiently do this, because essentially all you do is you kind of increment the pointer, access the memory, do whatever you need with it, and then essentially check whether the pointer has reached some point, right? If you are a tiny bit smarter, you will actually figure out that, oh, this loop, it doesn't matter in which order the iterations are done, because I can do them from the other direction. So basically initialize the counter to the top element, and then essentially do the same thing, but now compare against the base address of the array, which I have anyway, because that's what I read first. So essentially I'll read that into a register, initialize another. So I'm still using two registers, but I had to use them anyway, because to compute the last address, I would have to get the base address into another register anyway. So essentially, rather than kind of start from there and keep incrementing and have another register to kind of wait for it, I'm kind of still using two registers. And then you have things like oh, but what if I'm actually not using the index in any way? What if something just needs to be done 1,000 times, but basically there is no use of the index in a loop? If that's the case, then yeah, the compiler will basically say, oh, nobody's really using the index, so I can do whatever I want as long as there is 1,000 iterations, in which case it's much more efficient to basically load it with 1,000 and then compare to 0. That way I don't need a register to compare against. Basically, I need a counter register, but I don't need a second register. So if my loop is in need of more registers to implement the code in the loop, basically I have one more register available. So the compiler will also typically be able to do that. What compilers are typically not able to do is figure out, for example, that the way this code is written doesn't have to be that way. So basically, the kind of the higher level logistics of the code. So for example, sometimes the compiler, let's say you have a list of some sort, right? So for example, the compiler doesn't know what the structure of your list really is. All it sees is pointers, right? So things of that nature are actually something that the compiler really will not be able to figure out. Like for example, you maybe know how many elements the list has, but the compiler doesn't. So basically, in that case, the compiler cannot implement a loop that goes to 1,000 simply because it has to implement like a while loop that essentially checks the pointers and stuff like that. Whereas you maybe know that such a list always has some number of elements, or I do know the number of elements a priori. So basically, I can do something about that. Or oftentimes the compiler, for example, doesn't know that, especially for C, basically, because some of the C arrays are malloced. So I mean, there is a size to them, right? But as far as the compiler is concerned, it doesn't know the size a priori. So basically, it doesn't know what to use as the size of the array. But you may know it. So the things that programmers typically can do is basically write the code so that essentially rather than write the code so that it's kind of efficiently implemented in assembler by direct translation, you can kind of write the code in a way that the kind of compiler's simple pattern matching things can actually recognize and optimize, right? Which basically means that for example, keeping the expressions relatively straightforward, as in like all of the math is basically just kind of strided accesses and stuff like that. The compiler is really good at optimizing that. The compiler is not that good at optimizing anything that has kind of more complicated data structures and stuff like that. So for example, for a lot of algorithms like list sorting, let's say you have a list and you want to sort it, right? Very often it's actually more efficient to just take the list, flatten it out into an array, sort that, and then basically kind of recompose the list. Why? Well, because your array sorted, it's now these like nice expressions that the compiler can understand, like array indexing and stuff like that. The compiler basically can figure out a lot about indices and whether they are overlapping and stuff like that. But once it comes to pointers, the compiler still can figure out some things, but it's much more restrictive there. one of the biggest problems that the compiler basically has in trying to is in kind of understanding your code is it knows that in an array things with different indices are different things, but for pointers, it doesn't know whether two pointers point to the same location, and it's some of the most advanced optimizations are capable of proving some properties of pointers regarding that, like which pointers are for sure not pointing to the same location. But basically, if the compiler thinks that two pointers are maybe pointing to the same location, then essentially it needs to implement the operations that you're doing in exactly the order that they're done, because it needs to work in both cases. It needs to work in case the pointers are different, but it also needs to work in the case that the two pointers are the same. So for example, if you take a pointer and like star A is divided by 2, and then star B is add 1 to it. If the compiler can prove that A and B pointers are different, then it can basically reorder these operations or schedule them in a much, it can use them to fill gaps and stuff like. So basically, it can do optimizations with them. But if it thinks that A and B might be actually the same address, then it's forced to actually implement these operations in exactly that order. Basically, the star B thing has to happen before star A, because if A and B are the same, then first we need to double, then we add 1, not the other way around. Right. So very, very often you have these kinds of situations where basically, for the sake of kind of we humans basically try to, especially we programmers, try to essentially write this really compact code, even kind of abstract away something and kind of write this kind of really elegant code that basically does the right thing no matter what, but it uses pointers and stuff like that to do that. And very often that's actually counterproductive, because basically by doing, unless you're really transforming a lot of work into little work, in which case it's kind of you are optimizing the code. But if you're really doing that purely for the sake of kind of writing this in 5 lines, not in 10, it might actually be counterproductive, as in the 10 lines, because it's kind of explicitly laid out what's going on, the compiler actually may be able to do transformations that with the 5 lines that are kind of, more abstract, let's say, the compiler basically just doesn't have the capability to reason about some of its properties anymore, and thus it is forced to basically schedule instructions in a more restrictive way, as in it's not gonna write worse code than what you wrote. The problem is basically that if you write relatively simple code, the compiler might be able to actually optimize it a lot. But if you write complicated code, the compiler more or less will just keep what you wrote. If you see what I mean. Another set of, for example, transformations is basically when most of the optimizing compilers nowadays, for example, if you have, let's say you're iterating over a matrix, that's a very common thing people do, just kind of iterate over a matrix by kind of do for I equals 1 through number of rows, for j equals 1 0 through number of columns, just go through the matrix, right? So the order if you're actually going to access elements of the matrix, for example, the order in which you do the i's and j's is actually important. It's called a row major or column major order, right? And the reason why this is important is because of cache blocks. So basically, caches have blocks. Once you access an element of A, you are really, if you have a cache miss, the cache now gets that element of A, and also whichever elements of A are of the array are actually in the same cache block, right? So if what you're doing is basically, if you're accessing the array in order in which is it stored in memory, then basically you have a miss, and then for the next few elements you're guaranteed to have a hit because you're accessing the same block. And your traversal of the array essentially is only using one block at a time. In the cache, essentially, I fetch the block, I use it fully, then I need to fetch the other block. If the whole array fits in memory, then in my next iteration, I'll actually reach and kind of it all fits, and from then on, it's nice, right? But if the array doesn't fit in memory, at least I get, let's say 8 elements of the array fit in a cache line. At least I get 1 miss per 8,
element, right? Because, and I'm only really, even if I have like a one block of cache for this, I still will get like only 1/8 is misses, right? If you do the iteration in the opposite order, meaning you kind of go against the grain of how this is stored in memory, then basically you fetch a block just to use one element, and then essentially the other elements are, let's say, in the other columns, but you are first gonna, iterate over columns, right? I mean, but you're first gonna iterate over rows, right? So essentially you access, column 0, row 0, right? And then let's say that the other elements in the same cache block would be column 0, row 1, column 0, row 3, and so on, right? But you say, oh, but I'm not gonna, because I have for all the rows, and then for all the columns within that, I'm gonna change the column now. So next, what I access is C1, row 0. That's a different block, right? So you have a miss again. And the idea is that if you manage to fit an entire column of memory in the cache, then you will have your hit later when you switch to the next row and process everything, because the whole row worth of blocks is fit in the cache. But if the cache is too small for it, for example, if it's a level 1 cache and your array is pretty big, what's going to happen is basically by the time you reach the end of the column of all the columns, you have started replacing some of the blocks you fetched earlier. So when you go back to it, that block is gone. You have to refetch it. So now suddenly, like, every single access is a miss if you have something like that. And so again, like, some of the optimizing compilers are able to understand this and switch the order of loops for you. But in order to do that, it needs to be pretty clear to them that you can do that while preserving correctness. So basically do like for I equals something to something, for j equals something to something, then you have some sort of a body of the loop. It needs to be pretty clear to the compiler that if I reverse the order of looping for i's and j's, nothing changes as far as the end result of the loop. Typically, the compiler doesn't really understand a lot of stuff. What it does understand is that if every element is accessed once, and basically it understands that look, in every iteration of the loop, we are accessing a different tuple of ij. Like there is no pair of ij that is the same for 2 iterations of the loop, right? And then if every iteration of the loop essentially just accesses something of ij and doesn't do much else with I and j, then everything is fine, right? But if you start doing math with it and do like I plus 1, j plus 1, and so on, then the compiler, especially if you do something like you use both I plus 1 and also I in the same body of the loop, then the compiler can get confused and say, oh, okay, I mean, so it may be the case that you're somehow accessing, both the ij element of the array and also one of the other elements of the array, in which case the order of iteration starts to matter. Because it doesn't know exactly what the pattern is. So it says, okay, if I iterate in a different order, you might get a different result. Whereas you as a human understand that that's never going to, that actually you can reverse the order of iteration. In which case, it's kind of, it's a very nice, rule of thumb is basically like whichever language you're using, learn what is the order of storing rows and columns of arrays, and just whenever you write a loop that goes kind of the ij loop, basically just always do it in the right way, right? That's kind of the easy way kind of to fix this problem, but it requires you to kind of at least learn this. The less easy thing is but like more portable, so you don't have to like know for each language, for each architecture and stuff like that what's going to happen, is basically to know like, okay, there are some things that the compiler is likely to figure out, there are some things that it's unlikely to figure out. Let me write the code in a way that makes it kind of as plain as can be, right? Which for example, I've seen a lot of code where there are like 2 or 3 things that need to be done on a matrix, and the programmer went through like a lot of thinking to figure out how to cram all of that into one loop that iterates, kind of you iterate over i's and j's and somehow do all 3 pieces of work in the loop, basically. And the idea is that way I only iterate kind of over the array once and perform all 3 pieces of work. But it turns out that in most cases, you end up with like less performant code than when you basically just say, okay, I'll do the first piece of work, then the second piece of the work, with 3 different sets of loop nests, essentially. Why? Well, because For the first loop nest, the compiler says like, oh, this is a trivial operation. I'm just incrementing the elements of the array by one. Oh, then the next one is like, oh, this is a trivial operation. Just sum up the rows of the arrays and stuff. But whereas if you do all of that, basically the code may be too complicated, and the compiler not only cannot figure out what you're doing, it's also basically that suddenly it is not sure about some of the properties that would allow it to do optimization. The most recent kind of frontier for optimization is, for example, like using GPUs and stuff like that. And it turns out that if you do something really simple, it is highly likely that the optimizing compiler will actually know how to just offload that to the GPU if there is a lot of work there. It's not worth it to offload to the GPU if there is not a lot of work, but if it's like quite a bit of work and you are just doing something like iterate over a matrix and do something, the compiler is likely to determine that like, ooh, a GPU could do this, much faster than the processor because it has much more bandwidth, and this is just streaming over the array. That's what GPUs are good for and stuff like that. And essentially just implement this as 3 pieces of GPU code that are going to be done, like 10 times faster than if it was done on the processor. But if the code is structured in a way that it's like, oh, this kind of complicated thing, I'm not even sure whether the GPU can be done on the GPU. And for example, if it sees that, oh, every iteration is independent of each other. The GPU has a lot of these programmable elements. I'm just going to split the array and just have the 1,000 GPU things do them. I mean, the PEs on the GPU do them in parallel. You end up, with something that is way better than making a processor go over it, one at a time, right? But if the compiler cannot determine that it's for sure that the iterations are independent of each other, then it cannot do that. And that's where basically this kind of not knowing essentially what hardware might be used and what the compiler is typically capable of really helps, because basically if you have an algorithm that is of course you don't do any of this if it's something that consumes like 0.1% of the execution time, but basically if you're writing something that needs a lot of work of this kind, it's worth kind of thinking, I can just write it in a way that makes it plain and simple for the compiler to figure out that this is just a lot of work, but the pieces of work are independent of each other. It's basically kind of like, rather than for I equals 0 through 1,000, you kind of are trying to say basically for all i's do this, regardless of what the order of i's is, right? And then let the compiler figure out how's it going to do that.
Very cool. Thank you so much.
Yeah. I mean, it's totally like funny, nowadays. For example, like some of the things people do to kind of optimize code that are actually like not really optimizing code. So for example, people will very often do things like like the pound defines for expressions in C and stuff like that. And why? Well, because they don't want to have a function that is, you can have like a small function that does that work and call it, but they don't want to do that because that means you have to deal with a function call implementation, which basically pays the overhead of call and return and stuff like that. I mean, one of the simplest optimizations in compilers is inlining. So basically, the compiler, if it sees a tiny little function, and it can prove that that's equivalent to just inlining the code, it's going to do that. But the nice thing about writing the function as a function is that you get the benefit of type checking and stuff like that your defines are not. Plus, you don't have to deal with like slashes and stuff like that. I mean, basically in C and C++, doing defines that are like multi-line defines, basically, I mean, it's completely unreadable code, basically, whereas writing it as a function is, much, much cleaner, and pretty much anybody who can read C code can figure out what your function is doing. But typically in old projects, you will see that they have these enormously large defines for basically what should have been a procedure, simply because they kind of thought like, okay, this is part of some sort of a code that needs to be efficient, and this is going to make sure that this code is kind of written into the code of the function rather than created as a function call, and then I don't want to pay the overhead and stuff like that. In fact, the compilers are
much smarter about inlining than we humans tend to be, because the compiler is, kind of not lazy as we are. So basically, when we inline things, we will still kind of copy paste the code and then, replace some things and stuff like that. But we will not figure out, for example, that, oh, this is a constant. Like if you call it this way, then this becomes a constant and stuff like that. But the compiler will try all of these things. So essentially, you take a function, you inline it. If it was called with a constant parameter, the compiler will do what's called a constant propagation, which means basically replace all instances of A in the expression with like 1, because it is 1, and that allows you to do another optimization, because suddenly you don't have to assume that A can be any value, which means that you can now, for example, some instructions can only operate on, like small constants. If it is a small constant, you can implement it with a single instruction rather than do an expression and stuff like that. Typical things, for example, multiplication. The compiler can figure out that you're actually multiplying with like 4, 8, or 16 or something like that. Then it basically can do that way more efficiently than if you actually have like a real number there. Even for relatively big values, basically, because some of the 64-bit multiplications essentially need to be implemented as kind of several rounds of 32-bit, depending on the architecture. But some of the architectures, for example, don't really have native support for 64-bit integers or 128-bit integers, so you have to kind of implement that with kind of multiple rounds of multiplication of smaller width, right? But if you have a general, multiply huge integers kind of a thing, but in fact, sometimes you are using one of the numbers as a small number, then the compiler can very easily figure out that, oh, this is actually a matter of integer. I don't need to implement this as a, unsigned int 128-bit. I can implement that as 128-bit times like a 32-bit value, which is way more efficient and stuff like that. So for example, like function inlining and stuff like that are one of the things that typically we don't have to do manually anymore, just because the compiler has gotten pretty good at that. If we do something, we can do. I mean, there are pragmas and stuff like that that kind of suggest to the compiler this is like try to inline this or something like that. But you kind of get the benefit of basically having normal code, being able to debug it, test it, and stuff like that as kind of. And you can think of it as basically call this function and implement it, but for the sake of efficiency, it's going to be implemented in a way that works for the kind of how the low-level stuff is working. And one of the nice things about that is the code becomes more portable, because basically if you have written something in terms of 32-bit integer chunks and stuff like that, if you have an architecture that is actually capable of 64-bit integer processing, suddenly your code becomes really inefficient, because the architecture is actually capable of doing 4 times less work in terms of multiplication, right? But for some, so basically this is where you kind of really want to leave it to the compiler as much as you can. Okay, so if you have like any more questions, let's quickly do that, because it's already I've kind of talked for a long time, so I'm just like, if you have any other questions, let me know.
I'm good.
Okay.
Thank you so much for your time.
So you're still the only one in the episode, so I guess we'll just have a good week, and now that you're recording this, I just want to have like, hey, beware of like the projects and stuff like that are gonna be due soon, and we're coming up. I mean, the summer session is like really rapid, so basically keep in mind that pretty much at any given time we are not really too far away from needing to submit a project or do an exam and stuff like that. So it's like kind of we've just finished the meeting and stuff like that. I mean, the final is not too far away, so everybody should be really like trying to. I mean, if you're kind of lagging behind a little bit, definitely catch up. Definitely try to do the last project a little bit ahead of time, so that you actually have some time to study for the midterm and revisit some of the lessons and stuff like that. Okay, so that's it. Thank you for attending, and for everybody who might be watching, and see you next week. Thanks.